at several examples of applications of matrix operations. Imagine a cable company that offers internet service and they have three levels of service: pokey, adequate, and lightning. Matrix W shows the number of packages sold to homes and businesses from the West Office, and Matrix E shows the number of packages sold to homes and businesses from the East Office. Notice there are 4,000 homes choosing the pokey service, 18,500 choosing the adequate service, and 12,750 chose the lightning service. Whereas the businesses, there were 250 choosing pokey, 2,850 choosing adequate, and 3,400 choosing lightning. That was from the West Office. The East Office had 2,625 homes choosing pokey, 22,450 choosing adequate, 24,000 choosing lightning, and in terms of businesses, 180 in the East Office chose pokey, 3,500 chose adequate, and 4,200 chose lightning. What is the size of both matrix W and matrix E? Well, each of these matrices have 2 rows and 3 columns, and so the size is the number of rows by the number of columns. So we say that the size is 2 by 3. So what is the result of adding matrix W to matrix E? Well, first of all, we cannot add matrices unless they are the exact same size. They need to have the same number of rows and the same number of columns. And that's because you add like terms. You always add like terms. In this case, we're going to add like locations. Row 1, column 1 will get added to row 1, column 1 of the other matrix. Row 1, column 2 will get added to row 1, column 2 of the other matrix, etc. So the homes choosing pokey service in the West get added to the homes choosing pokey service in the East. The homes choosing adequate service in the West get added to the homes choosing adequate service in the East. The homes choosing lightning service in the West get added to the homes choosing lightning service in the East. The businesses choosing pokey service in the West get added to the businesses choosing pokey service in the East, etc. So if I add the like locations, 4,000 plus 2,625, I get 6,625 in my sum. If I add 18,500 to 22,450, I get 40,950. If we add 12,750 to 24,000, I get 36,750. The 250 businesses choosing pokey added to the 180 businesses choosing pokey. That is a total of 430 businesses between East and West choosing pokey. And if I add the 2,850 to 3,500, I get 6,350. And lastly, 3,400 added to 4,200 gives me 7,600 or 7,600. So when you add matrices, they have to be the exact same size and you add like locations. Usually in an application, that also means you're adding like categories. Here, homes get added to homes, pokey gets added to pokey, adequate gets added to adequate, etc. Now suppose the company offers rebates and free weeks of service as incentives. Matrix R shows this information. For pokey service, you get a rebate of $50 and 4 free weeks. If you choose adequate service, because it's going to cost a little bit more, you get a rebate of $100 and 6 free weeks. If you choose lightning service, you'll get a rebate of $250 and 12 free weeks. What is the size of this matrix? Well, we have 3 rows and 2 columns, so it is a 3 by 2 matrix. Now, since matrix R is a 3 by 2, I can multiply W or E or W plus E by R if I multiply in the order of the 2 by 3 multiplying the 3 by 2. I can only multiply matrices if the columns of the first match the rows of the second. So if I take W plus E, which is a 2 by 3, and I multiply in the order W plus E times R, where R is a 3 by 2, I will get a 2 by 2 matrix as a result. Remember, when you're multiplying matrices, you are treating the first matrix as if it has row vectors and the second matrix as if it has column vectors, and you're finding dot products. So I dot the first row vector with the first column vector. I dot the second row vector with the first column vector, etc. So here, if I take the first row and I dot it with the first column, I will be taking the 6,625 homes that chose Pokey service and multiplying it by the $50 rebate, and then adding it to the 40,950 homes that chose adequate, multiplying it by the $100 rebate, and then the 36,750 homes that chose lightning service get multiplied by the $250 rebate, giving me $13,613,750 that were given to homes as a rebate. If I dot the first row with the second column, I'm taking homes choosing Pokey times 4 weeks of free service, adding it to the homes that chose adequate times 6 weeks of free service, plus the homes that chose lightning times the 12 weeks of free service, giving me 713,200 weeks of free service to homes overall. Now, when I dot the second row with the first column, I get $2,556,500 given to businesses as rebates. And if I dot the second row with the second column, I get 131,020 weeks given away to businesses free. Again, when you're multiplying matrices, you're treating the first matrix in the product as if it has row vectors, and you're treating the second matrix in the product as if it has column vectors. So the number of columns of the first matrix has to match the number of rows of the second matrix. But just because you can mathematically multiply two matrices when you have an application does not necessarily mean that the result makes sense. If we had mistakenly multiplied R by W plus E, we would have been able to do that mathematically, but it would not have given us something that made sense. We would have been multiplying the $50 rebate by the number of homes that chose Pokey and adding it to the 4 weeks of free service multiplied by the number of businesses that chose Pokey. And adding rebate to weeks of service doesn't make sense. You can't add things that are not like terms. So adding money to weeks of service and you're mixing up the homes and the businesses, it just would not make sense. However, if we multiply them in the order that we did, where we multiplied W plus E times R, that gave us something that made sense. We went across the homes and down the rebates for the homes. And then we went across the homes and down the weeks of service for the homes. Then we went across the businesses and down the rebates for the businesses, and across the businesses and down the rebates for the businesses. That ended up giving us something that made sense. $13,613,750 was given in rebates to homes. The total rebates for businesses was then the $2,556,500. And we had a total of free weeks of service for the homes of 713,200. And then lastly, the number of free weeks for businesses was 131,020. Let's look at another example involving adding matrices. Suppose a plane is flying at 540 miles per hour at a bearing of 290 degrees. Bearings are measured from north, so what we might picture as the positive y-axis, and you rotate clockwise if you're talking about bearings measured from north. So you go through the quadrant to east, then south, then west, and back to north. The wind is blowing at 42 miles per hour at a bearing of 30 degrees. The meteorological department is predicting that the wind velocity is going to increase to twice its speed. To fly more safely in the wind, the plane plans to decrease its speed to 90% of the current speed. Write this situation as a scalar multiple of sums of vectors. Also find the resultant speed and bearing of the plane, given that it's adjusted for the wind. Let us first find the components of the plane's vector and the wind's vector. A bearing of 290 degrees measured from north is coterminal to the angle of 160 if we measured from the positive x-axis counterclockwise. So the components of the plane's vector is the 540 miles per hour times cosine of 160 degrees for the x component, and then 540 times sine of 160 degrees for the y component. The wind had a bearing of 30 degrees. That's coterminal with a 60-degree angle. So the wind's components are 42 times cosine of 60 for x and 42 times sine of 60 for y. Now, the meteorological department is predicting that the wind speed is going to increase to twice its speed. So 2 times the wind vector would be 84 times cosine of 60 for x, and then 84 times sine of 60 for y. The plane is going to fly more safely by decreasing its speed to 90% of the current speed. So 90% of the plane's components will be 0.9 times the 540 times cosine of 160 and the 540 times sine of 160, giving me 486 times cosine of 160 for x and 486 times sine of 160 for y. So the result will be 2 times the wind vector added to 0.9 times the plane vector. Adding these two vectors together will add x components, and then we'll add y components. So the 84 times cosine of 60 degrees added to the 486 times cosine of 160 degrees gives a decimal value of approximately negative 414.6906 for the x. Adding 84 times sine of 60 degrees to 486 times sine of 160 degrees gives us a y component of 238.9679. Remember to have your calculator in degree mode if you are double checking this on your calculator. So that's our resultant vector. It's pointing in what we might consider quadrant 2. If we are measuring bearings, though, we're going to need to remember to measure from north. Let's first find the resultant speed. So the resultant speed should be the magnitude of that vector. So the magnitude would be the length of it. I am using Pythagorean theorem, and I am squaring the sides of the right triangle where the length of the vector is the hypotenuse. So the resultant speed will be the square root of the 414.6906 squared added to the 238.9679 squared. And that gives us a speed of approximately 478.6167 miles per hour. So that would be the result of the plane being affected by the wind. Now, to figure out the bearing, let's first find the angle that this vector is making with the negative x-axis. So the y is one side of a right triangle, the x is the other side of a right triangle. So The y would be the opposite side, the x would be the adjacent side. So tangent of the angle would be the 238.9679 over the 414.6909. Inverse tangent of that ratio gives me 29.9529 degrees, or about 30 degrees. That is measured from the negative x-axis. So the bearing will be 270 degrees plus that angle, or 299.9529 degrees, or basically 300 degrees. So the plane is flying now at a bearing of about 300 degrees at a speed of 478.6167 miles per hour. In example 3, we're going to look at an application of multiplying matrices. A large rock is being moved for a garden art installation. The rock is moved by a machine with 3 forces. Force 1 first moves the rock from 0, 0, 0 to the position 8, 42, 10. The components of force in that case is 108 pounds for the x direction force, 90 pounds for the y direction force, and 20 pounds for the z direction force. Then force 2 moves the rock from that second position, 8, 42, 10, to the position 2, 56, 14, x, y, z respectively. And the components of that force are 68 pounds in the x direction, 48 pounds in the y direction, and 15 pounds in the z direction. A third force then moves the rock from that position of 2 feet, 56 feet, 14 feet, to a final position of 18 feet for x, 64 feet for y, and 16 feet for z. The components of that third force are 80 pounds in the x direction, 75 pounds in the y direction, and 12 pounds in the z direction. Form a matrix of the force vectors, and then a second matrix of the position vectors. And in physics, the definition of work is force times distance. So in the physical world, work means force times distance. So this would be an application where we will multiply our matrices to calculate work. The units of work in this case will be foot-pounds because we're measuring distance in feet and the force in pounds. And the work, or the physics work being done, will end up being the values on the diagonal. And the other entries of our product will not have any practical meaning. So only the diagonal values need to be found because they're the values that only have some practical meaning. So be aware of that sometimes you could multiply matrices and have some of the components, usually it would be the diagonal, have some meaning, and some of the other components, if you analyze the units, wouldn't necessarily have a practical meaning. It doesn't mean that multiplying the matrices wasn't useful. It just means you need to be careful analyzing your units. So always watch your units and see whether or not your operation gives you some practical meaning. Notice in setting up our matrices, the first matrix has the forces, and I've made my rows the first force, the second force, and the third force. The second matrix has the positions, and I've made the columns the positions. Now we started off at 0, 0, 0, and then we moved to what is called P1, and that first position after we moved by the first force had an x component of 8, a y component of 42, and a z component of 10. We then move to the position 2, 56, 14. So I know that the x went down 6 from 8 to 2, but we're interested in the distance moved. And so you don't want to treat that as a negative 6. Instead, you want to treat it as a positive 6 because you don't want to lose the energy that it took to move from the 8 to the 2. So ignore the fact that the x went down by 2 in that move from 8:42:10 to the point 2:56:14. So again, I'm going across the force rows, down the position columns as I multiply. So the dot products are shown here, 108 pounds times 8 feet added to 90 pounds times 42 feet added to 20 pounds times 10 feet, etc. And again, only the diagonal ends up making sense. If I took the second row and multiplied it by the first column, I would be applying force 2 to the first motion, but force 1 caused the first motion, so again, that doesn't make sense. So only the values on the diagonal end up making sense in this application. So when we get finished, we have the information that the first force did a total amount of work of 4,844 foot-pounds. The second force did a total amount of work of 1,140 foot-pounds, and the third force did a total amount of work of 1,904 foot-pounds. Matrices can be used plentifully in robotics motion programming. So here's an example in which we have a 24-inch robot arm is being programmed to move. The robot arm initial point is located at 0, 0, 0, and its terminal point where the hand is located is positioned at 10, and then the square root of 220 is the y component, and then 16 for the z component. Your assignment, if you wish to accept it, is to rotate the arm 160 degrees counterclockwise around the z-axis, 20 degrees counterclockwise around the y-axis, and 60 degrees counterclockwise around the x-axis. This could be accomplished as 3 separate matrix multiplications on the original position vector, or you can multiply the 3 correct rotation matrices and then apply that to the position vector. We'll clearly state the 3 correct rotation matrices, and will clearly state the final position of the terminal point of the arm after all of the rotations. And of course, we can use our calculator to complete this because the numbers are pretty messy. Now, it might be helpful to have the information that if you're trying to rotate in 3-dimensional space around the x-axis, the following matrix will give you that rotation, where the first row, first column has the value 1, and then the rest of the first row and the rest of the first column are zeros. And we then have a little 2 by 2 taking up the second and third rows and columns, where I have cosine of the angle I'm rotating minus sine times the angle I'm rotating for the rest of the second row, sine of the angle I'm rotating, cosine of the angle I'm rotating make up the rest of the third row. And then similarly, if I'm rotating around the y-axis, my first row will be cosine of the angle I'm rotating, and then 0 for y, sine of the angle I'm rotating for z in the first row. Then my second row is 0, 1, 0, and the third row is minus 1 times sine of the angle I'm rotating, 0, and then cosine of the angle I'm rotating. Again, these are counterclockwise rotations around the axes. And then for z, the matrix has first row cosine of theta minus 1 times sine of theta, 0. The second row has sine of theta, cosine of theta, 0. And the third row is 0, 0, 1. And that is the matrix that gives you rotation around the z-axis. Again, assume counterclockwise rotation. So for a 60 degrees counterclockwise rotation around the x direction, a 20 degrees counterclockwise rotation around the y-axis, and 160 degrees counterclockwise rotation around the z-axis, we have the matrices presented in the top of this slide. You can individually take each of those matrices and multiply by the original position. So first rotate around the z-axis, then rotate around the y, then rotate around the x. Or you can multiply those three rotation matrices together and then apply it to your original position of 10x, 14.832y, and 16z. Whether I individually apply or multiply them all together, I get a final position of negative 8.125 for x, negative 22.566 for y, and 0.883 for z. So matrix multiplication is very common in programming robots to move just like you want them to. So those are just a few examples of applications of matrix operations. Realize that you need to pay careful attention to the units and always think through what the arithmetic is doing with those units. Sometimes you get a very practical, useful meaning, sometimes not. Remember the one example where only the values on the diagonal had some practical meaning. But this opens your eyes a little bit to how helpful matrices can be.